Hey there, and welcome to The Explainer. Today, we're going to talk about one of those components that's absolutely everywhere in electronics, but can be a little weird to wrap your head around. The inductor. They're in your computer's power supply, your phone's wireless charger, you name it. But how they do what they do is kind of counterintuitive. So let's break it down. So to get us started, let me ask you a question. In the world of electronics, what component acts like a big, heavy flywheel? Something that really resists any sudden change in motion. Well, you probably guessed it, it's the inductor. And this whole idea of electrical inertia is really the key to understanding everything else. Okay, so what's the textbook definition? An inductor is a passive component that stores energy in a magnetic field when current flows through it. A resistor just burns energy off as heat, and a capacitor stores it in an electric field. The inductor's whole game is the magnetic field. But to really get a feel for how these things work, we need more than just a definition. Let's try to build a mental picture of the inductor as, like, the most stubborn, change-averse component you could possibly put in a circuit. The engineering mindset has this fantastic analogy that I love. Imagine water flowing through pipes, right? Okay, step one, you turn on the pump. Water wants to rush through, but bam, it hits this big, heavy water wheel. At first, the wheel just doesn't want to move, so the water slows way down. But as the pump keeps pushing, the wheel slowly, reluctantly starts to spin. It gains momentum, faster and faster, until it's at full speed. And at that point, it's hardly resisting at all. Now, here's where it gets really cool. What happens when you suddenly turn the pump off? Well, that wheel has so much inertia that it just keeps spinning, and it actually pushes the water forward, keeping the flow going for just a little bit longer, even with no pump. That is exactly what an inductor does with electricity. So, the single most important thing to remember is this. Inductors hate change. They absolutely hate it. When current tries to ramp up, the inductor pushes back. When current tries to drop, the inductor pushes forward to keep it going. They just want everything to stay nice and stable. Okay, that water wheel idea is a great way to think about it. But if you're an engineer actually trying to use one of these, you've got to be able to speak the language of the datasheet. So let's see how all this reluctant behavior is actually measured in the real world. Now, when you first crack open an inductor's spec sheet, you're going to see a whole bunch of numbers. But for almost any design, there are really four big ones you have to pay attention to: inductance, DC resistance, rated current, and saturation current. First up is inductance, that's the L, and it's measured in henries. This is its main job description, right? A higher inductance basically means you've got a heavier, more stubborn water wheel. It can store more magnetic energy, and it's going to fight against changes in current way more aggressively. All right, now we get to two numbers that trip people up all the time: rated current and saturation current. First, let's look at rated current. This one is all about heat. It's a thermal limit. It tells you how much current you can push through this thing before it physically gets too hot and, maybe cooks itself. Saturation current, on the other hand, is a totally different beast. It's a magnetic limit. It has nothing to do with heat. It's about performance. It's the point where the inductor's core is magnetically full and it just stops acting like an inductor. And that idea of saturation, that's where we leave the nice, clean textbook world behind. See, an ideal inductor would work perfectly no matter what. But real ones, they have a breaking point, and that breaking point is called saturation. So what's actually happening here? Well, you can think of the inductor's core like a sponge for magnetic flux. It just soaks it up until it can't soak up anymore. It's completely saturated. And when that happens, its ability to be an inductor, its inductance, just falls off a cliff. It pretty much stops working. And you can see this perfectly here in how different materials behave. Some cores, like gapped ferrite, have what we call sharp saturation. The inductance is rock solid, and then, boom, it just plummets. But other types, like power cores, have a soft saturation. The inductance sort of gracefully bows out. And knowing which one you're dealing with is absolutely critical for reliable design. So what's the actual damage when this happens in a circuit? Well, check this out. The blue line shows how current should rise in a perfect inductor. It's nice, linear, and predictable. But those orange and yellow lines, that's what happens in the real world. As the inductor saturates and its inductance collapses, the current suddenly starts rising much, much faster. It's a runaway train. And that out-of-control current can easily fry other parts of your circuit. But here's the really cool thing about engineering. A limitation like this imperfect behavior, it's not just a problem to design around. It's an invitation to get clever. It actually drives innovation. Let's look at how engineers took a classic headache and turned it into a brilliant solution. So here's the dilemma.
Imagine you're designing a DC to DC converter, which are in pretty much every piece of electronics you own. You have this classic trade-off. You can use a small inductor, which gives you a super fast response when the power demand suddenly changes, but you get a lot of noise or ripple on your power line. Or you can use a big inductor. That gives you really clean, low noise power, but it's slow to respond to changes. You could have fast, or you could have clean. You couldn't have both.
So what was the fix? It was genius. Engineers stopped thinking about just one inductor and asked, well, what if we use two, but we link them together magnetically? This is what's known as a coupled inductor. By getting them to share a magnetic field, they could do things that no single inductor ever could. And the results are just wow. Look at this. On the left, with standard inductors, you see that jagged, noisy waveform. That's all that ripple we were talking about. Now look at the right. With the coupled inductor, that same waveform is unbelievably smooth. That is a massive win for efficiency and clean power.
But wait, what about the response time? That was the other half of the problem, right?
Well, that's the other part of the magic. On the left, with the old way, you see the voltage takes a big dive and then slowly recovers. But on the right, with the coupled inductor, look at that. The dip is way smaller and the voltage just snaps right back where it's supposed to be, super fast. So what we have here is the absolute best of both worlds. You get the super clean power of a big inductor, but you also get the lightning fast response of a small one. A classic you can't have both engineering problem, completely solved by understanding the physics a little bit better. So, why does any of this really matter? Well, it's about more than just some cool components. It's about understanding the clever compromises and the hidden innovations that make all of our modern technology even possible. So let's wrap up with the key takeaways. First, inductors are like electrical flywheels. They resist change by storing energy in a magnetic field. But they're not perfect. They have this very real limit called saturation, where they just stop working right. This imperfection creates huge design challenges for engineers. But, and this is the cool part, it's by wrestling with those limitations that brilliant solutions like coupled inductors are born. And really, understanding these components is absolutely fundamental to designing the efficient power supplies that run literally everything we use. And that kind of leaves us with one last thought to chew on. We just saw how the very limitation of a component forced engineers to come up with something even better. It really makes you wonder, doesn't it? What other imperfect components out there, the ones that don't quite behave like the textbook says they should, are secretly shaping the technology we'll be using tomorrow? Thanks for watching.